This is a practice exercise from page 103 in your textbook. We're learning how to calculate theoretical yields and then percent yields. These problems can also be part of limiting reactant problems, like from the previous videos, so it's possible you'll have to go through a full set of calculations in order to determine the limiting reactant, in order to determine the amount of product produced, to use that to make your theoretical and percent yields. This problem is a little bit easier for us because they're telling us what the limiting reactant is. Since they're telling us what the limiting reactant is, we don't really have to go through the whole setup of an ice table or anything like that. We know that the iron oxide is our limiting reactant, so we can just use that number, the 150 grams, in order to calculate how much product is formed. They're essentially telling us that the carbon monoxide is an excess reactant, so we really don't have to worry about that. So that means that this is a pretty straightforward problem. They're giving us the amount of starting material, and they want to know the yield of iron. Again, before I start any problem, I want to have a game plan. I want to think through what my calculations are going to look like. I know that I'm starting with grams of iron oxide. The only thing I know how to change grams into is moles. I do that using the molar mass or the molecular weight from the periodic table. I know that I'm ultimately going to want my answer in terms of iron. So I'm going to change it from moles of iron oxide to moles of just iron using the coefficients from the reaction. You need to have a balanced reaction, so always check and make sure your reaction is balanced before you use the coefficients. And then with a theoretical yield, I typically do this in grams. So I'm going to change my moles of iron into grams of iron, again using the molar mass or molecular weight from the periodic table, and that is going to be just for iron. So now that I understand what the process is going to look like, I can go ahead and start these calculations. I'm starting with 150 grams of iron oxide. I want to cancel out the grams so I can be in units of moles. Calculating the molar mass, I know that 1 mole is equal to 159.6 grams. Remember that we're rounding everything to 1 decimal place. Then I'm going to cancel out my moles of iron oxide because I really just want moles of iron. In order to do that, I look at the balanced reaction. I see for every 2 moles of iron that are formed, I consumed 1 mole of iron oxide. And again, we do want to put that 1 in when we do the stoichiometry so we can clearly see the mole ratio. Last thing we're going to do is get rid of the moles of iron because we want grams of iron. And again, using the periodic table, we should see that there are 55.8 grams for every mole. So watching our units cancel here, grams of iron oxide canceled, moles of iron oxide canceled, moles of iron canceled, leaving us with grams of iron, which is what we want. In this case, we're going to assume that this number has 3 significant figures. It's kind of iffy with the 0 at the end. It kind of looks like it has 2, but in this case, your textbook says it has 3, so we're going to go ahead and use 3 just so the answer matches up with what's in the textbook. So our answer to 3 significant figures is 105 grams of iron. So this should look really similar to the stoichiometric calculations we're doing before. The only thing that's different is we're attaching this word theoretical yield to it. So a theoretical yield tells us how much of a product we should theoretically make if everything goes perfectly. So essentially if all of my reactant turned completely into products. So if that happened, if all 150 grams of iron oxide turned into iron, I should have 105 grams of iron at the end of this reaction. But we should know that from real life, when we do these experiments, we don't often have a 100% or a pure theoretical yield. Instead of getting the 105 grams, we may only get 87.9 grams. So that is an actual yield. Now, calculating a percent yield is actually a pretty straightforward calculation. The way this looks is that a percent yield is equal to the actual yield, so what you did get, over the theoretical yield, what you were supposed to get, and since it's a percent, we're going to multiply it by 100. Now, in this case, for this problem, they are very specifically telling us what the theoretical yield is, so we just calculated that theoretical yield, and they are very specifically telling us the actual yield. If they don't use those terms in the problem, the theoretical yield is always what you calculate using stoichiometry. So we did the calculation to get a theoretical yield. It's what we are supposed to get. The actual yield is what actually happened. The way you would get an actual yield is they may tell you that in the course of a reaction this many grams were produced, and if they tell you that's what did happen, that's what makes it your actual yield. So theoretical yield, always calculated from stoichiometry. Actual yield is either given in the problem or something you measure in the lab. So let's go ahead and insert the values that we know. So in this case, our percent yields, we actually got 87.9 grams. We should have gotten 105 grams, multiplying that by 100 to turn it into a percentage, and we get a percent yield of 83.7%, rounded to 3 significant figures. So this tells us that the reaction is only 83.7% efficient. We were supposed to get 105 grams, but we only got 87.9 grams.